2015 Physics Senior External Exam, Paper 2, Question 3. Let's read and identify. A trampolinist uses the elastic energy of the trampoline and energy from their legs to achieve significant heights. An 80 kilogram person, we have a mass, stands on a trampoline and sinks down 20 centimeters. We have a distance. Let's make the distance meters right now as we read the question. Given that the trampoline is 120 centimeters off the ground, so we've got an initial height here of 1.2 meters for the trampoline, and can be depressed to the ground, so 1.2 will be the maximum extension. What is the maximum height above the ground that the trampoline alone could project the person? We must draw a diagram here so as to understand exactly what's happening. And I'm going to treat my trampoline as a spring, and so we have our trampoline at rest position. Here is the rest position. When an 80 kilogram person hops on our trampoline, you can see that the extension here is 20 centimeters. So it has an extension from the rest position. If I continue the rest position over, 0.2, when a mass of 80 kilograms, so if we use F equals m times g, 80 times 9.8, let's calculate 80 times 9.8 so that we can get an accurate reading for the force. The force of gravity is 784 newtons. Now this will enable us to draw a force extension graph, and if we draw a force extension graph, then we're able to calculate the constant for the spring. For an extension of 0.2, a force of 784. Now this is F equals k times x is the equation of this line. So therefore the gradient of our line, which is our spring constant k is given by F over x, which is 784 divided by 0.2. 784 divided by 0.2, you can see I've still got that in my calculator, 3,920. So that is our 3,920. That is our spring constant, and it is Newton per meter. So Newton on the top line per meter. So Newton meter to the -1. Now for the second part. Given that the trampoline is 1.2 meters off the ground, and that's the maximum extension, we can now draw our trampoline at a maximum extension here of 1.2 meters. So therefore, given that as our maximum extension, we can work out what the energy stored in the trampoline must be at this particular point. So a half times k times x squared is how we work out the energy stored in the spring, or if you like, we extend this graph here to 1.2 and we work out the area underneath the graph at 1.2. A half times k, 3920, multiplied by 1.2 squared. We can go through, we can work that out. Now I've still got the 3920 in my calculator from before, so we divide that by 2, we go equal, and we multiply it by 1.2, and we multiply it by 1.2. So that's a total energy there of 2,822.4 joule. Now that's the energy stored in the spring. That energy then is then transferred to kinetic energy when the mass of the person returns through the rest position, and then the person leaves the trampoline and goes up in the air. So at maximum height, the total energy is all gravitational potential energy. Now this spring potential energy here, this is the total energy when that's at the bottom of its motion. Now at the top of its motion, the total energy is given by plus the kinetic energy. Now at maximum height, that's 0. So this is what we need to work out, mgh. So mgh is equal to 2822. Mass is 80 times 9.8 times h. So I need to solve this now. Now I've still got my answer in my calculator. So if I divide by 80 and I divide again by 9.8 and I go equals, you'll get a height of 3.6 meters. Up a little bit, there we go. Height is 3.6 meters. Let's go through and just check to see whether that makes sense. They've gone down 1.2 meters. They've gone up 3.6 meters. Yeah, 3.6 meters is a relatively accurate, appropriate answer.